Hi everyone, today we're going to do the 2018 AP Calc AB free response question, and this is going to be number 4. So this is one of the no calculator questions, so you can't use a graphing calculator, and we'll see that this is one of the fairly typical table problems where they give you a table of data and ask you questions about it. So let's dive right in. Number 4 says, the height of a tree at time t is given by a twice differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h of t are given in the table above. Okay, so notice they're not giving us the actual equation for h of t, but they do tell us that the function h is twice differentiable, meaning it has a first derivative and a second derivative, so that might be important in the problem. And they're only giving us some particular values of the function in this table. Okay, so first it says, use the data in the table to estimate h prime of 6. Using correct units, interpret the meaning of h prime of 6 in the context of the problem. Okay, so since again, we don't have the function, we can't actually take the derivative. If we want to estimate this derivative, we're going to estimate it as the average rate of change on an interval that contains 6 in the middle. So in particular, 6 is between 5 and 7. So I can approximate h prime of 6, the instantaneous rate of change at 6, by the average rate of change at 6. Sorry, this is t equals 6, not x. And that average rate of change is just the slope between the 2 points. We have the point 5, 6 and the point 7, 11. So this is going to be like h of 7 minus h of 5 over 7 minus 5, which is 11 minus 6 over 2, which is 5 over 2. So this is our estimate for h prime of 6, and now we have to interpret the meaning of this and the units. So we would say, well, this is estimating the rate of change of the height at time 6. So we'd say at time t equals 6, the rate of change of the height of the tree is about 5 halves. And what are our units? Well, the top units, the h values, their units are in meters, and the time is in years. So this is 5 halves meters per year. Great. Okay, that's part A. Part B. Explain why there must be at least one time t between 2 and 10 such that the derivative of t is 2. Okay. Because they want us to show that there must be at least one time, this is what's called an existence statement. We're showing that some existence, I might have spelled that wrong. Sorry if I did. Existence statement. And there are 2 main theorems, I would say, or perhaps 3, but usually 2 that are used, that are existence statements that say that some time, some x value exists that has some property. And those are the intermediate value theorem or the mean value theorem. And the main thing to note about one of the main things to note about the intermediate value theorem is that the intermediate value theorem tells you something about the actual function. This one would be about h of t. And the mean value theorem tells you something about the derivative of the function. So because we want to know a time exists where the derivative has some value, we want to use the mean value theorem. Okay, so first question, can we actually use the mean value theorem? We need to be able to satisfy the hypotheses. And the answer is yes, because our function is twice differentiable. That tells us that it's also continuous. So since h of t is differentiable, it is continuous on 2 to 10 closed. And it's differentiable on the open interval in particular. I mean, it's differentiable everywhere, I assume, because they don't tell us it's not. It's continuous, and so we can apply the mean value theorem. So by the mean value theorem, I'm just not writing it out to save time and space, but you should probably write this out on the actual test. So by the mean value theorem, there exists at least one time t where, okay, now what? Well, the mean value theorem says that there exists a time where the derivative is equal to, so where h prime of t is equal to the average rate of change on any interval that's within your region where you know your function is continuous and differentiable. So in particular, now we're looking for an interval between 2 and 10 where the average rate of change is 2. Okay, so I'm going back up to the top and I'm looking for my slope between any 2 points. They don't actually have to be next to each other. You know, it could be between like this point and this point. But I want my average rate of change, my slope between those points, to be 2. And so it doesn't take too long, hopefully, to notice that between these 2 points, we go up by 2 in the t's, and we go up by 4 in the h's. So 4 over 2 is 2. So in particular, we have at least one time where h prime of t is equal to h of 5 minus h of 3 over 5 minus 3, that average rate of change, the slope there, which we just saw was 4 over 2, or 2. So then we're done. That's it. That's the reason. Okay, part C. Use a trapezoidal sum with 4 subintervals indicated by the data in the table to approximate the average height of the tree over the time interval 2 to 10. Okay, so first of all, what are we trying to find? Average height. Whenever you see average of a function, you should think average value of the function on that interval. So remember that this average height on this closed interval, 2 to 10, is going to be given by 1 over b minus a times the integral from a to b of the function. So in our case, that's 1 over 10 minus 2, the integral from 2 to 10 of h of t dt, which is 1 over 8, this integral. And now what they want us to do is they want us to approximate this average height by approximating this integral using a trapezoidal sum. Okay, so now we want to approximate this integral from 2 to 10 of our function, approximating it by a trapezoidal sum using the data. Okay, so whenever I'm doing any kind of Riemann sum, right, left, trapezoid, whatever, I find it easiest to not make mistakes if I plot out the data. Now, your plot does not have to be exact. The axes don't have to actually be, to scale or anything like that. But plotting the points and drawing the actual rectangles or trapezoids, I find is helpful for not making mistakes. So I've got 2, 3, 5, 7, and 10. 5, 7, and 10. And my heights are 1.5, 2, 1.5, 2, 6, 11, and 15. Great, and now I can actually draw my trapezoids using these 4 intervals that they give me, trying to find the area of these 4 trapezoids. And the first one has area given by, great, so I'm trying to find the areas of these trapezoids. And now that I've drawn that out, hopefully it'll be easier to see exactly what that is. So remember that the area of a trapezoid is given by the average of the bases. So 1/2 the sum of the bases, that's just the average of the base heights, times the height or the width. And now remember, in this case, our bases are these vertical sides, and our height is actually like the width. Okay, so for us, the first one, we have our heights are 1.5 and 2, and our width is the distance between 2 and 3, which is 1. So 1.5, 2, so this is 1/2 the sum of 1.5 plus 2 times the width, our height was 1. The next one, we've got heights 2 and 6 and width 2. So 1/2, 2 plus 6 times 2. The next one, our heights are 6 and 11 with width 2. 6 plus 11 with 2. And the last one here is 11 and 15 with, so 11, 15 with width 3. Okay, and now we just have to add all of this up. So let's see how good my mental math or computational math is. This first one, I'm going to change 1.5 to 3/2. I think fractions are easier. So this is 3/2 plus 2 is 4/2. So I have 7/2 times 1/2. So 7/4 for this first term, the area of that first trapezoid. The next one, the 1/2 and the 2 cancel, so that's nice. I'm left with 8. Again, the 1/2 and the 2 cancel, so I'm left with 17. And then we've got 11 plus 15 is 26. Divided by 2 is 13. 13 times 3 is 39. Okay, so now I've got 39 plus 25, the 8 and the 17, 64. So I have 64 plus 7/4, so I need to multiply by 4 to get this over fourths. So this is 6, 1, 24, 25. Okay, so 256 over 4 plus 7 over 4. So I'm adding 7 now to this. We have 3, 1, 263. Okay, so this is 263 over 4. And that's our trapezoidal sum, which approximates the area from 2 to 10 under our function h of t. And we wanted to use that to approximate the average height. So remember, now I need to multiply by this 1/8 to get the average height. So this implies that the average height is approximately 1/8 times 263 over 4, which is 263 over 32 And our units, since this is the height, was measured in meters. That's our answer. Finally, part D. The height of the tree in meters can also be modeled by this function g of x, where x is the diameter of the base of the tree in meters. When the tree is 50 meters tall, okay, so if it's 50 meters tall, that means g of x is 50. The diameter of the base of the tree is increasing at a rate of 0.03 meter per year. Okay, so diameter, remember that's x, increasing at a rate, that means it's the derivative. So what this is telling us is that dx dt, the derivative with respect to time, at that time is 0.03. According to this model, what is the rate of change of the height of the tree with respect to time? Okay, rate of change of the height. That means the height is g. We want the rate of change of it, so we want dg dt in meters per year at the time when the tree is 50 meters tall. So we want to know this. When g of x is 50, and we know that at that time dx dt is 0.03. So you see how the first battle of this part of the problem is just identifying, translating all of the verbal statements into mathematical statements. Remember, rate is always going to indicate a derivative, in this case with respect to time, so that's dt. Great. So now, well, they give us an equation for g. So if I'm trying to find dg dt, I need to take the derivative with respect to time of my g equation. And, well, the thing to notice is that g is a function of x, not a function of t. So when I do this, this is really the same as like taking the derivative of g with respect to x first, and then multiplying by, then taking the derivative of x with respect to t. This is chain rule here. And so what do we get? Well, dg dx, I should use quotient rule since it's a fraction, or you could rewrite it and use product rule if you brought the 1 plus x to the numerator. But I'll just use quotient rule. So we've got low d high minus high d low times 1 over the square of what's below. So 1 plus x squared. That's the way I remember the quotient rule. Low d high plus high d low, low d high minus high d low, all over the square of what's below. And we need to multiply that by our dx dt, which we know is 0.03. Okay. And so now we need to compute this where, well, what do we know? We know that g of x is supposed to be 50. But I don't need g of x to calculate this number. I need x. So I better take my equation for g of x and set it equal to 50 and solve for x. So this gives me 50 plus 50x equals 100x. Subtract the 50x over, 50 equals 50x. So x is equal to 1. So now I just plug in 1 everywhere. So I've got 2 times 100 minus 100 times 1 over 2 squared is 4. I'm multiplying all of that by 0.03. So this is like 200 minus 100 is 100. So we've got 100 over 4 times 0.03. I'm purposely not simplifying this because 100 times 0.03 is just 3. So this is 3/4. So this says that the rate of change of the height of the tree with respect to time, dg dt in other words, is 3/4 meters per year at the time when the tree is 50 meters tall. And that's it for problem number 4.
Don't forget to subscribe and hit that bell for all future notifications.